Do you know this person? Yes, he is Newton. Newton has left behind many achievements in various fields. His most well-known works are the discoveries of the equation of motion and the concept of the universal gravity. In this lesson, we will conduct an experiment on the universal gravity. The universal gravitational force acts between all objects. You may know that the universal gravitational force between two objects can be expressed like this. The universal gravitational force that we feel on the surface of the Earth is the so-called gravity. In this experiment, we will measure the gravitational acceleration, g. If the mass of the Earth is m and the radius of the Earth is r, the gravitational acceleration, g, is expressed by this equation. Since the Earth is rotating, centrifugal force is also acting on the Earth's surface in addition to the universal gravitational force. The acceleration due to this combined force is observed as the gravity. Considering these factors, it should be noted that the gravitational acceleration depends on the height and the altitude of the measurement point. There are two main methods to measure gravitational acceleration. One is to let the object fall freely in an environment where air resistance can be ignored, such as in a vacuum, and measure the acceleration directly. The other method is to measure the period of a single pendulum to indirectly determine the acceleration. In this experiment, we will use the second method. First, let's consider the motion of a single pendulum. As we all know, the motion of a weight, m, attached to a string of length, h, can be expressed by this equation. When the swing angle, theta, is small, the weight obeys a simple harmonic oscillation. The period, t, of a single pendulum is expressed in this way. From this equation, we can estimate the gravitational acceleration, g. In this experiment, we will use a Borda pendulum. This is a device invented by Borda. In order to improve the accuracy of the period measurement, it is necessary to measure the period many times. However, with a simple pendulum like the one shown on the left, the vibration quickly decays due to friction and deformation at the fulcrum. In the Borda pendulum, the fulcrum is a knife edge to reduce friction. However, if the oscillation period of the knife edge is different from the period of the whole pendulum, it becomes a coupled oscillator and does not vibrate monotonously. A Borda pendulum is one in which the periods of the knife edge and the period of the entire pendulum are same. Then, the whole pendulum vibrates as one. If the knife edge and the weight are connected with piano wire, the change in length is also reduced. Since the structure is simple, the equation for the oscillation period is also simple. If the length of the piano wire, L, and the radius of the weight, R, are defined as shown in the figure, the oscillation period of the Borda pendulum, T, can be expressed by this equation. The gravitational acceleration, g, is expressed by the following equation. We can see that we need to measure the period, t, the length of the piano wire, L, and the radius of the weight, R. In this measurement, we are aiming for an accuracy better than 10⁻³ power. To achieve this, we need to carefully consider the error of each measurement. How much of a difference in gravitational acceleration does our target of 10⁻³ power correspond to? The difference in gravitational acceleration between Sapporo and Kagoshima is about the same. Also, if we look at the difference in height, the difference in gravitational acceleration between the sea level and the top of Mount Fuji is about the same. Let me introduce the parts of the Borda pendulum used in this experiment. This is the iron ball used as a weight. This is the knife edge. We connect the iron ball to the knife edge with a piano wire. You should have a piece of wire cut to the right length. This is the knife edge support stand. There is an adjustment screw to make the knife edge horizontal. Now let's assemble the Borda pendulum. First, connect the iron ball to the piano wire. Remove the screw from the iron ball with a screwdriver. and thread the piano wire through the hole in the center of the screw. Bend the end of the piano wire with long nose pliers. The length of the bend should be about 2 to 3 mm. If it is too long, it will protrude from the screw. Return the screw with the piano wire through it to the iron ball, and tighten it firmly with a screwdriver. Next, fix the other end of the piano wire to the knife edge. There is a cross cut on the end of the knife edge like this. Loosen the screw to open the cross cut. Once the piano wire is threaded through, tighten the screw to secure it. If it is not tightened properly, the piano wire will slip out and the length will change during measurement. Tighten the screws firmly. Now, place the knife edge support and knife edge on the table on the wall or beam. Before you do this, you need to make sure that the knife edge support stand is level. The support stand is more than 2 meters high, so you will need to climb up on a stepladder to do this. When using a stepladder, please observe the following precautions. Do not stand on the top of the stepladder. Do not step over it. Do not sit on the top board. Do not lean forward. Try to work in front of your body as much as possible. When using a stepladder, face the front of the stepladder from the second step down and place your shin on the top board or treadle to stabilize your body. This is a spirit level. It contains liquid and air bubble. If the spirit level is leaning, the bubble will move toward the higher side. When it is level, the air bubble is in the center. You can use this to level the support stand. First, place the level like this. There are 3 screws on the support base, and you need to adjust it with these 2 screws first. Now, place the level at a slight angle and adjust it with another screw. Repeat this process several times to level the knife edge support. Once the knife edge is placed on the support, the assembly of the Borda pendulum is complete. Next, take a test measurement. Pull the weight slightly and release it. Swing the pendulum about 10 times and measure the period of the pendulum with a stopwatch and your eyes. At this point, remove the piano wire from the knife edge. Now we need to adjust the oscillation period of the knife edge to the period of the whole pendulum, but the period will be quite short if we don't adjust the knife edge because of its short length. First, widen the left and right screws. Now, check the balance between the left and right screws, and adjust them if they are tilted. To make the oscillation cycle even longer, move the top screw up. However, if the center of gravity is higher than the fulcrum, it will not vibrate, so be careful. Next, measure the period of the knife edge by swinging it alone. Adjust the period so that the difference between the oscillation period of the knife edge alone and the overall period is within 10%. Once adjusted, connect the weight to the knife edge again. Measure the length, L, from the top of the weight to the knife edge. At this point, it is difficult to put the scale exactly parallel to the piano wire, but please think carefully about how to measure with trial and error. In this experiment, we will use a device called a photogate to measure the period of the pendulum. This device, which shape looks like a letter U, is a photogate. The light passes between this part and that part of the gate. Place the photogate on a height-adjustable lab jack and adjust the height of the photogate so that the center of the weight blocks the light. If the weight blocks the light, the weight is considered to be passing through the gate. If the amplitude of the pendulum oscillation is too small, the weight will remain blocking the light and the period cannot be measured. Connect the photogate to the interface with a dedicated cable. Connect the interface to the PC with the supplied USB cable. For detailed instructions, please read the operation manual distributed to you. Now, let's start the measurement. Pull the weight slightly and gently release it. At this time, make sure that the vibration plane of the weight is orthogonal to the knife edge. This is an example of swinging at an angle. If you let it swing diagonally, the trajectory will eventually become an ellipse. Make sure that the weight always passes through the same position of the photogate. If the measurement data is not symmetrical or has two peaks, the pendulum is not swinging monotonically. Eliminate the cause why this is the case. After finishing the measurement, measure the length, L, from the knife edge to the top of the weight again. Make sure it has not changed from before you started the measurement. Finally, measure the diameter of the weight. Note that the diameter of the sphere is the diameter of the great circle. If the point where the caliper touches is not on the great circle, the measurement result will be smaller than the diameter. Use this equation to find the gravitational acceleration, g, from the measurement results. The report should summarize the following, but please refer to the text for more details. This concludes the explanation. Now let's start the experiment.